The first thing to note is that all the pies cost an integer amount, that's a whole number. And then writing these words mathematically, we have the cost of a cherry pie is the same as 2 apple pies. I can write that equation. The cost of a blueberry pie is the same as the cost of 2 damson pies. And then a cherry pie cost plus the cost of 2 damson pies is the same as the cost of an apple pie and 2 blueberry pies. And I'm interested, like Paul buys one of each type. So what I'm interested in is A plus B plus C plus D and what that could be equal to. There's more than one possible answer, but one of them is going to work here and the rest are not. So we have simultaneous equations essentially, not enough to be able to find each thing for sure, but we do have 3 with 4 unknowns and we can still use substitution to get some information about some of them. So I'm first of all going to replace this C here by 2A. I'm going to eliminate C to get it in terms of A. So 2A, I'm going to keep the D there. 2D equals A, and then I'm going to eliminate B. And I can do that by replacing it by 2D. So I'm going to get 4D. And if I minus A from both sides, minus 2D from both sides, I get A is equal to 2D. And the good thing about this is that now I have the cost of a blueberry pie in terms of a damson pie and the cost of an apple pie in terms of a damson pie. So if I can get the cherry pie in terms of damson pie, then I'm sorted. And we can do that by substituting back in actually into here. So it must be that C plus 2D is equal to A, which I can now replace by 2D, plus 2B. That's 4D. And these are going to cancel. I've got that the cherry pie is 4 times a damson pie. And that is all I need because I'm going to get 2D plus 2D plus 4D plus D. That's the cost I'm interested in. And that's going to be 9D. So it must always be a multiple of 9. So we can't solve these equations, but we can get certain bits of information. Must be a multiple of 9, and the only one that works is B. So that's our answer. Now that is the best approach to solve this question, but I do want to talk about another way that would have worked. And that is to basically create a table of possible values for A, B, C, and D. We know they're all integers, so we just need to check them as we go along. So let's, for example, try A is equal to 1. Then because C is equal to twice that, it must equal 2. And then we have this equation here in terms of that relates C, D, A, and B, which I could rewrite as A minus C is equal to 2D minus 2B. We also have, in fact, that B is equal to 2D. So it could be tempting to just replace that and get it'd be minus 2D as the answer. And therefore, I'm just going to make another part of my table just here is A minus C, and here it would be minus 1. Now, there's no way that I can make D an integer and do minus 2 times it to give minus 1, so that's not going to work. I can rule it out, which takes me on to my next one. A is 2. Then C would be 4. A minus C would be minus 2. And this time D would have to be 1, and this would work. Remember, B is equal to twice that, so this would be 2, and that would be a possible solution. 2 plus 2 plus 4 plus 1 is 9. That could have been an answer. Of course, it's not there on the list, so we'd have to keep going. Maybe let's try 3, and then C will become 6. We'll get minus 3 for A minus C. Again, this isn't going to work. I can't, D must be an integer. There's no way that I can do minus 2 times D to give minus 3, where D is an integer. So then A is 4, C is 8, that will give minus 4, which must mean that minus 2D is minus 4, we'll get D is 2, and then B must be 4. These add to give 18, and that is on the list, so we would know to stop. So actually you can sort of see from here it's coming out that it's always a multiple of 9. It's just a different approach where I didn't explicitly show that. It just came out when I drew the table. So it's decent if you don't see the other answer. But anyway, hope you're happy with this question.